Welcome back to the workshop. Module 5 is an overview and discussion of the rigid pavement design strategies. Module 5 overviews and discusses the rigid pavement transfer functions and models and how they are used to design rigid pavements using the PMED design software. This session of Module 513 focuses on smoothness degradation of jointed plain concrete pavements. For smoothness degradation, the same type of information will be discussed as was included for mid-slab cracking and faulting of transverse joints in jointed plain concrete pavements. There are 3 learning outcomes of Module 513 on smoothness degradation. They include explaining the design premise for smoothness degradation of jointed plain concrete pavements, defining the smoothness degradation predicted in the PMED design software, and describing the regression equation for defining smoothness degradation. Starting with the definition and measurement of smoothness. Smoothness is defined as the variation of surface elevations within the wheel path that induce vibrations in vehicles. Smoothness is quantified by the International Roughness Index, or IRI. IRI is simply the sum of cumulative movements in one direction between an axle and a body of a standardized vehicle. IRI is a mathematical index of the longitudinal profile of the road expressed in meters per kilometer or inches per mile. IRI has been adopted as a standard measure of smoothness by the Federal Highway Administration and many individual state highway agencies. IRI is used to quantify smoothness in the PMED design software for jointed plain concrete pavements. Smoothness in the PMED design software is used to predict pavement functional performance of a jointed plain concrete pavement from a highway user's perspective. Smoothness is measured in accordance with AASHTO R43M and AASHTO 43-07, which is the standard practice for quantifying roughness of pavements. It can also be measured in accordance with ASTM E1926, which is the standard practice for computing the International Roughness Index of roads from longitudinal profile measurements. The IRI is computed using profile measurements from devices such as the inertial profiler, the dipstick, as well as from rod and level surveys. The devices commonly used to measure smoothness include high-speed inertial profilers, as well as the lightweight, low-speed inertial profilers. The next section of this submodule is to overview the distress mechanism or the design premise approach used to determine the deterioration or degradation of smoothness after initial construction, or simply the increase in IRI over time. Smoothness degradation, or the increase in variability in the pavement profile, point by point in the wheel path, over time is not predicted using mechanistic empirical concepts. The approach or method used or applied in the MEPDG manual of practice was simply to develop a statistical model or regression equation to determine the change in IRI from field data, which include key factors such as the initial IRI, increases or changes in structural distress over time, and site factors to account for subgrade differential movements, climate fluctuations, aging, surface degradation, and other such factors. The smoothness generalized model, or the generalized regression equation, is displayed on this slide. The IRI is predicted over time and is based on the initial smoothness, initial IRI after construction, the distresses measured or predicted over time, and the site factors, which include or can include freezing index, percent passing the number 200 sieve, average rainfall, and other type of climatic and soil factors. And then the regression constants, A and B, of the dependent variables. So the IRI was predicted over time based on the initial IRI, a combination of site factors, and then how the distresses increase over time. The next portion of this submodule is to present and discuss the regression equation for calculating IRI throughout the design period based on the design premise for a jointed plane concrete pavement design strategy. The jointed plane concrete pavement smoothness degradation regression equation is included on this slide. The IRI is calculated using the percent cracked slabs, the average total faulting of transverse joints, the percentage of joints with medium to high severity spalling, and the site factor. The calibration coefficients of the regression equation are listed on this slide. The percent cracked slabs coefficient is 0.446. The coefficient for the percentage of joints with spalling in the medium to high severity is 0.373. The faulting of the transverse joints constant is 0.993, and the site factor coefficient is 46.422. The values for the calibration coefficients or constants may vary between different publications of the MEPDG manual of practice depending on the results of any updated global calibration process. The coefficients of the transfer function or regression equation are also included in the output report for the pavement ME design software. The site factor, the SF or site factor variable of the smoothness degradation regression equation is included in this slide. The independent variables of the site factor include the age, pavement age in terms of years, freezing index in terms of degree Fahrenheit days, and the percent of subgrade material passing the number 200 sieve. So pavement age, which is a coefficient, the freezing index, Fi, and the percent passing the number 200 sieve. The scaling factor variable of the Spaulding equation is included on this slide. So the percentage of joints with medium to high severity spalling are defined by a scaling factor equation. So the spalls is included is the age in the exponent, and then a scaling factor equation to determine the coefficients of spalling. The scaling factor equation is simply this equation here, or regression equation shown on the slide. Air PCC is the entrained air of the concrete mixture. Preform, or the preform factor, is the type of sealant used in the joint. A 1 is for preformed sealants, and 0 is for no preformed sealant. F'C is simply the concrete compressive strength at 28 days. FT cycles, or freeze-thaw cycles, is the average annual number of freeze-thaw cycles. Age is the pavement age in years. HPCC is simply the concrete slab thickness. And WCPCC is simply the water-cement ratio of the concrete mixture. This slide summarizes the coefficients that were used to calibrate the coefficients from the calibration process of the regression equation or design premise for predicting the IRI throughout the design period for jointed plain concrete pavements. The calibration coefficients include, which were summarized in previous slides, they include C1, which is the cracking coefficient of 0.446. C2 is the spalling coefficient of 0.373. C3 is the faulting coefficient of 0.993. And C4 is the site factor coefficient of 46.422. Reliability was discussed in detail in Module 3 and how reliability is applied and used in the pavement ME design software. The standard deviations of the residuals are very important for determining reliability, and the standard deviation of the residuals for the Jpcp smoothness is displayed on this slide. The standard deviations of the residuals is used to determine the reliability as related to smoothness of jointed plain concrete pavements. This section is a summary of the materials presented under Module 513 for jointed plain concrete pavement smoothness degradation. The three learning outcomes from Module 513 on smoothness degradation included explaining the design premise for smoothness degradation of jointed plane concrete pavements. We defined the smoothness degradation predicted in the PMED design software, and we described and explained the regression equation and the coefficients within the degradation for calculating smoothness degradation throughout the design period of jointed plane concrete pavements. This ends Module 513 on Jpcp Smoothness Degradation. The next submodule of the training course sequencing is Module 514 on the jointed plane concrete pavement interpretation and adjusting design features and factors to achieve an acceptable design strategy.